Okay, let's get started. So today it's my pleasure to welcome Georgia Karagiorgi from Columbia University, who will tell us about her adventures in machine learning with reconstruction of neutrino events. So please go ahead, Georgia.
Great, thank you so much. Let me share my screen. So let's see, I'll do this. And then I do slideshow. Can you see the slides okay?
Yes.
And I controls. Okay, great. So yes, it's my pleasure to give this talk on machine learning applications for fundamental physics discovery with high-resolution particle imaging detectors. So I understand that this seminar is aimed to be given to a rather broad audience. So for those of you not familiar with what I'm referring to when I talk about fundamental physics, what I mean is the way that nature works at its most basic or small scale. So this scale is much smaller than the scale of than the atomic scale. It's the subatomic world scale. So imagine an atom, a tenth of a nanometer. Within that, orders of magnitude smaller, 5 orders of magnitude smaller is the nucleus. Even smaller than that is a proton or a neutron within a nucleus. And even that is not an elementary or fundamental particle of nature, but instead its composite quarks are. So when we talk about fundamental physics, we're referring to the study of elementary particles, which are the fundamental building blocks of matter around us, and the particle interactions that are that these particles experience, which themselves are thought to be mediated by other virtual particles. So in particle physics, which is this field that allows us to study this way that nature behaves at the smallest scales, we have a theoretical prescription that allows us to, with very high accuracy and high precision, be able to predict particle behavior and nature's behavior, both at microscopic but also macroscopic scales. So this theory is very predictive and expandable. And in this standard model of particle physics, much like in the periodic table of elements for the case of chemistry, fundamental particles or elementary particles are arranged according to their properties, their intrinsic properties, their quantum numbers, into different groups. And so we have the quarks and leptons, which make up the basic constituents of all matter, visible matter around us, as well as these mediator particles or the force carriers, the particles that allow these particles to interact with each other through either electromagnetic or strong or weak interactions. And there's an additional particle, the Higgs, which interacts with all of the elementary particles which carry mass, and it's responsible for ascribing these particles their masses. Okay, so how do we study these particles? Well, a lot of what we do in experimental particle physics is to construct giant devices, which are particle detectors, and allow us to see particles and how they behave when they interact with other matter that is also made of particles. And the typical processes which subatomic particles undergo and that we exploit to make particles reveal themselves in our detectors include processes like scintillation or ionization, where, for example, a charged particle that traverses a medium that's made of atoms can sometimes interact with, or as it traverses the medium, since it's charged, it will often impart enough energy to atomic electrons to kick them off their parent atoms, creating ions, liberating ionization electrons as ionization charge and leaving behind positively charged ions. But other times, this charged particle will simply impart just a little bit of energy to such atomic electron, bouncing into a higher bound state. And then once it goes back to its ground state, then it will lead to atomic de-excitation in the form of emission of a photon. And this is what can be detected as scintillation light from various, for example, organic materials. Other ways of detecting particles is through their emission of electromagnetic radiation in a way analogous to a sonic boom. When these charged particles travel in a medium, which is not a vacuum, with a speed larger than the speed of light in that medium. So that's called Cherenkov radiation, and it's another way that we exploit to infer the existence of a relativistic particle inside some transparent medium. And other times, the way that we can infer that a particle has traveled through our detector is by observing the aftermath of its head-on and typically very energetic collision with other matter, which in its turn can produce other visible subatomic particles, which are visible in our detectors through these processes again, ionization, excitation, or Cherenkov radiation. And this particular way of detecting particles is how we can actually study neutral particles, which cannot ionize and cannot excite as they travel through a medium, but every once in a while they can have a hard head-on collision with an atomic nucleus, for example, producing lots of other charged particles, which are then visible in our detector. So here is an example of that. So a neutrino is one of the fundamental elementary particles of nature. It is neutral and therefore can enter through some detector volume represented in this blue C over here in the microboon detector, and might interact in a head-on collision with an atomic nucleus in the detector. The result of that is the production of a number of charged particles in the interaction, the neutrino nucleus interaction, which then will stream out of the interaction point and leave a visible imprint behind. In this particular interaction, from data recorded by the microboon experiment, the type of interaction that is happening is a mu neutrino interacting with an argon nucleus, which we don't see neither of those as the initial state of the interaction. But what we do see is the final state of the interaction, which is the result of a number of protons kicked out of the argon nucleus, along with a corresponding flavored charged lepton. So mu neutrino because it becomes a charged muon, which is seen here by this long line. So these types of measurements of individual particle interactions are now very, very commonplace in particle physics. And by studying the aftermath of such energetic collisions is how we can study and test the standard model theory to very, very high precision, as often statistics and systematic uncertainties allow us. And through that, then we can better understand particle properties, particle dynamics, and underlying symmetries in nature. And to be able to study increasingly more rare and complex interactions like this, we also require increasingly higher resolution of our detectors, ability to see individual particle imprints like that, and sensitivity. And this allows us to probe increasingly rare and fainter signals. To do that, then we have to build bigger, typically, and more powerful instruments with higher granularity. And this leads to inevitably much higher volume of data generated from detectors, which we then have to process and sift through in order to study the events that we care about. So these pictures that I showed you in the previous slide are from a detector that recently completed its running studying neutrino interactions. The size of this detector, and I show here a zoom-in version of what's happening inside this detector, is about the size of a school bus. But a much bigger and more monstrous version of that detector is actually being planned for construction in the US, with anticipated start of operations as early as the end of the current decade. And so this is the Deep Underground Neutrino Experiment. It is a massive project, $1 billion scale in cost project, which will be based in the US. And what it aims to study, as the name suggests, is neutrinos. So all the way from Illinois, the world's highest intensity neutrino beam will be constructed and shot deep underground, all the way to South Dakota, where a detector the size of multiple buildings put together will be able to sample and measure neutrinos flying to South Dakota all the way from Illinois, using a detector technology similar to that of microBUNE, which is a liquid argon time projection chamber technology. And I'll explain in more detail in a later slide. So this experiment, called DUNE, is currently under early stages of construction. And the FAR detector will comprise 4 different sub-detectors, each one 10 kilotons in size, of liquid argon, cryogenic cold liquid argon detectors, which have the ability of imaging charged particles that are produced in neutrino interactions with the argon. So what is DUNE actually aiming to measure? Well, being deep underground, what that means is that DUNE is very, very well shielded from any kind of cosmic ray particles or any other particles that are produced, in the Earth's atmosphere, or even, charged particles produced in the Fermilab beam. The only thing that makes it to the detector is very weakly interacting particles like the neutrinos, which themselves travel through 800 miles of Earth unperturbed before making it to the detector. And then we look for some of these to interact in this massive 4-module detector over here. So one of the primary goals of DUNE is to measure these neutrinos from the Fermilab beam, and in particular determine their flavor composition, whether they are electron or muon neutrinos. The beam produces primarily muon neutrinos, so almost 100% of muon neutrinos when they're produced in Illinois at the Fermilab accelerator. And by the time that they reach the FAR detector in South Dakota, a non-zero fraction of these is expected to oscillate into electron neutrinos, and a lot of them into tau neutrinos as well. So what DUNE seeks to do is actually measure the flavor composition, both very close to the neutrino production, expecting mostly muon neutrinos, but also at this FAR detector, and measure the relative fractions of electron and muon neutrinos. And what this allows DUNE to do is to very precisely understand how neutrinos oscillate from one flavor to another. So this neutrino oscillation is a quantum mechanical effect that neutrinos exhibit. They can change from one flavor to the other as they propagate through space-time, because they are known to have non-zero masses. And the different masses that they come in are different admixtures of electron, muon, and tau flavor. So as these different masses experience time as they propagate differently, that leads to the quantum mechanical observation, the quantum mechanical effect, which can be observed as oscillations from one flavor to the other. Okay. So DUNE will be able to look for these oscillations and measure them for both a neutrino beam as well as an anti-neutrino beam. And comparing neutrino and anti-neutrino oscillations allows DUNE to determine whether neutrinos and antineutrinos oscillate differently. And if that is the case, then this bears implications about the matter-antimatter symmetries in nature. And in particular, it might bear implication as to why there is more matter than antimatter in our universe today. In addition to studying the differences between neutrino and antineutrino oscillations, DUNE is also sensitive to the possibility that one of the neutrino mass states could be the heaviest or the lightest. There's still an ambiguity given current experimental measurements, and theory allows for either situation at the moment. So this is referred to as the normal versus inverted mass spectrum. In addition to neutrinos from the world's highest intensity beam, which will lead to just a few hundred of neutrino interactions in the DUNE far detector per year, DUNE will also be able to measure neutrinos that are produced constantly in cosmic ray air showers in the atmosphere. So these are cosmic rays from outer space hitting nuclei at the upper levels of the atmosphere, and then producing a cascade of other particles which decay, producing neutrinos. And these atmospheric neutrinos actually extend over energies that are higher than those of the neutrinos in the beam. So this is a very nice and complementary sample for studying neutrino oscillations in addition to the beam, and where we expect on the order of a few thousand interactions per year in the DUNE far detector. In addition to these high energy beam and atmospheric neutrinos, DUNE will also be sensitive to neutrinos that can be produced from a potential nearby or galactic supernova burst. These are much lower in energy than atmospheric or beam neutrinos. And so this makes them much harder to see in the DUNE detector because they leave very faint, low energy imprints in the DUNE detector. But in the case of, let's say, a galactic supernova at about 10 kiloparsecs from Earth, then DUNE would expect to see up to a few thousand of neutrinos interacting in the entire far detector over the course of only 10 seconds. So it would be this magical show of fireflies going off everywhere within the DUNE detector volume. If we could see with our naked eyes, that would all go off within 10 seconds in an otherwise fairly silent detector. So it would be truly amazing if we were so lucky to observe this once a century type of an event of a galactic supernova burst in DUNE. And this would allow us to access information on supernova physics and dynamics, as well as on neutrino properties. In the case of supernova dynamics, I'm not an expert myself, but there are a lot of physics associated with the supernova explosion itself. So measurements of neutrino spectra, meaning how many neutrino interactions we see as a function of time, and how the average neutrino interaction energy evolves as a function of time in our new detector, has sensitivity to different, these spectra have sensitivity to different processes going on during supernova explosion. We have information during early times on the neutronization part of the supernova burst, then accretion, and then cooling as well. And so, for example, models that involve the formation of a black hole after a supernova explosion would lead to a noticeable effect in the number of neutrinos as a function of time after a fairly early time, about a couple of seconds, where all of a sudden neutrinos cannot escape the black hole horizon, and then we have a sharp cutoff in our supernova neutrino event rate. And there are other effects as well that we can probe associated with supernova physics and dynamics, collective effects, shock waves, strange star formation, standing accretion shock instability oscillations. And in the case of neutrino properties, even neutrino oscillations themselves affect the number of neutrinos that we expect during neutronization time. In particular, oscillations suppress the number of electron neutrinos that we expect from the supernova burst very early on, and they suppress that number much more so if the neutrino mass spectrum is normal as opposed to inverted. So being able to measure the flux of neutrinos as a function of time very, very precisely allows us to also tell things about the property of neutrinos themselves. Now, in addition to neutrinos, the DUNE far detector, being this massive detector that is very well shielded from other types of particles, offers the possibility of searching for other rare processes as well. For example, even the matter within the detector itself, the protons and neutrons inside the argon atoms of the detector volume. There are theories beyond the standard model of particle physics, so new physics theories that predict that these protons or neutrons might decay in a way that violates fundamental symmetries of nature. Now, this would be groundbreaking if we were to observe this. It's only predicted to happen very, very rarely, but the benefit of having such large, well-shielded detector deep underground is that you have Avogadro's numbers upon Avogadro's numbers of protons and neutrons that you can then hope to see one of them with some tiny little probability individually decay away. So these are all rare processes, and they're all of fundamental importance in nature, and they can be probed with an advanced instrument such as DUNE. So let me tell you how DUNE works, and therefore how it can study these interactions. So the DUNE far detector, these 4 modules themselves, are subdivided into individual cells. Each one represented here is about the size of a very tall room, 6 meters high room. And it's filled with liquid argon. And across this completely homogeneous large volume of liquid argon, what we do is we apply a very large and uniform electric field. And we instrument one side of this volume with sensor arrays, which are sensitive to ionization charge. So what happens is that every once in a while, you may have an incoming neutrino which creeps in to our detector unobserved, since it's neutral. It leaves no imprint behind, except for when it undergoes a head-on collision with an argon nucleus, and a number of charged particles can be produced. As these charged particles are produced, instantaneously they produce prompt scintillation light, but also as they travel and zip through the liquid argon, traveling with the speed of light, they produce and leave behind a lot of ionization electrons. They ionize along their trails. Now, this ionization, under the influence of this electric field, starts to drift very uniformly towards our sensor array. And if these sensor arrays are segmented finely and instrumented so that each one of the sensors is read out independently and continuously as a function of time, as this ionization charge distribution sweeps by the sensor array, the different arrays allow us to map out 2-dimensional projections of the ionization charge deposits as they are getting collected across the array, or as they induce signals as they pass by different layers of this array. So in the end, we end up with these stereoscopic 3D projection images of whatever is going on within this volume. And since these wires are being continuously read out, then this leads to a stereoscopic video capture of the activity within the detector volume with, depending on how closely packed together the sensors are, sub-millimeter spatial resolution. And in the case of DUNE, we have, just to get a sense of what kind of data rate this continuous video stream corresponds to, we have, for every module, for every one of the 4 modules, we have about 150 to 200 of these cell volumes, and each one of them, each one of them is read out in frames of 2.25 milliseconds, representing full projected views from different angles of this volume, with each frame being 11.5 megapixels in size, and with each pixel having 12-bit resolution. So this results into a total data rate of about 40 terabits per second, and DUNE is built to operate continuously, meaning streaming this video rate continuously for the duration of more than a decade. Okay, so what does DUNE actually see in this high streaming data rate? Well, this is an example of just one such 2.25 millisecond frame from just one of those 200 volumes that makes up the 200 cells that makes up one of the 4 detector modules. So for the most part, DUNE sees image frames in its video stream that look like this. And these are actually empty frames, okay? So this represents one of the 2D projected views of whatever is happening within the cell volume. And the color scale represents the energy deposition, which is proportional to ionization charge within the detector. And it looks like static. And this is primarily electronics noise and small energy deposits due to radiological impurities that exist within the liquid argon and spontaneously can radiologically decay, producing very small amounts of energy that then becomes visible in our detector. Now, among these continuous stream of mostly static noise, every once in a while, we might get these really spectacular and beautiful interactions of interest. For example, a neutrino that is produced in the Earth's atmosphere interacting in one of the cells might look like this, producing charged particles which travel tens of centimeters and leave their ionization charge imprints behind. Or cosmic rays, it doesn't happen very often, but some of them make it as deep underground through the rock, the overburdened rock, to the DUNE detector, and might look like these straight lines streaming through the detector as well. Or these rare beyond standard model neutron and proton decay processes might also look like this in the detector, extending tens of centimeters to about a meter each, and being fairly energetic, meaning leaving behind lots of ionization energy deposition represented by the red color here. So these are very easy to pick out from noise, although they are difficult to differentiate one from the other on an interaction by interaction basis. But on average, they can be differentiated based on their energy, the pixel intensity, and also their topological extent and characteristics. You know, how how extensive they are in space, what their shape is, are they more linear versus spherical? Are they made of just straight line tracks or showery objects? What is the track or shower multiplicity? Are those objects connected or detached, but in the vicinity of each other? These are characteristics that we make use of very, very frequently in trying to identify candidate interactions of interest, and especially in offline data processing. Now, what is more challenging than finding these relatively high energy signatures of interest in the DUNE streaming video is a supernova interaction from a supernova neutrino interaction from neutrinos from a supernova core collapse. So supernova neutrinos are very low energy, and when they do interact in the DUNE detector, they leave behind an imprint which is very small in extent, and it's very, very similar to ambient radiological background activity in the detector. I like to show these images. One of these contains a supernova neutrino interaction and the other one doesn't. I don't know if you can tell which one does and which one does not. Here I will show you. The supernova interaction is seen here as this slightly more noticeable red dot on top of this ambient radiological and electronics noise background. Now, these interactions are rare. They happen once per century, and DUNE is literally streaming thousands and thousands of these images per second. Now, among these images, DUNE can only afford to make a mistake, mistaking this as containing a supernova interaction, for example, only once every 10,000 times, while it has to maintain very, very high efficiency in actually keeping or identifying and tagging the frames that do contain a true supernova neutrino interaction. So this is a ridiculous challenge that DUNE has to meet. Now, if we find these interactions, we also need to save them. We need to save the corresponding data with sufficient resolution so that we can zoom in much, much, much more closely later on, in which case we will see, after we suppress lots of the ambient noise in the vicinity of that interaction. So this is zooming in now from a couple of meters to, this is a 6 centimeter scale. This is an example of a simulated supernova neutrino interaction event, where you can see from the neutrino interaction an electron that gets produced as a charged particle produced in the interaction of the neutrino with an argonucleus. And also these tiny little blips that you see here, which are de-excitation photons from nuclear de-excitation after the interaction took place. So these are even lower in energy than the electron and have a much smaller extent. And they're really only visible as blips in the vicinity of the interaction. So we need to be able to first find these supernova neutrino interactions, of which we might have just one or a few or thousands within 10 seconds over a given century. And then we need to zoom in closely in the interaction and reconstruct what is actually happening as part of the interaction. So this is a huge feat, but at the same time, the fact that we're dealing with a technology that offers high resolution and sparse images and also translationally invariant signatures of interest with unique topological features, and the fact that we're dealing with an application where we can actually design and simulate data, we have predictable data driven by physics principles, this actually makes DUNE, or liquid argon TPC detectors, as an ideal case for applications of machine learning, as well as particularly real-time AI. And I should add that these features are common to many particle physics experiments, not just the DUNE experiment or other liquid argon TPC detectors. There's other types of detectors as well that are making now increasingly heavy use of machine learning and AI for processing and analyzing their data. I'm actually doing this work as part of a growing community of particle physicists and in collaboration with computer scientists who are interested in integrating AI and ML with fundamental particle physics discovery. But there's, of course, many other national initiatives, including the IAFI Institute and also A3D3, as you all know, which are really pushing the envelopes in this direction. Okay, so in particular, liquid argon TPCs have seen huge successes in employing machine learning and AI for data analysis, but in particular for offline data analysis. What do I mean by that? It means that the data that contains the interesting interactions is already pre-recorded, and then we have the luxury of time and lots of computing resources to be able to analyze and reanalyze and examine and re-examine our data, and then apply these very computationally intensive machine learning algorithms on our data. But by doing so, we've actually demonstrated huge success in achieving excellent particle physics signal of interest reconstruction and selection performance, and extracting maximal physics information out of liquid argon TPC data. In this respect, the microBOON experiment, which already completed its running, has led several pioneering applications of machine learning or deep learning for LArTPC data analysis. microBOON has demonstrated that you could do object detection, for example, finding a neutrino interaction among ambient cosmogenic backgrounds in a detector that's operating on surface, or that you can identify pixels on the basis of whether they belong to an electromagnetic shower object or another charged particle track, a muon or a proton, for example, and as well as classifying objects according to their candidate type: electron, photon, muon, pion, proton. And these techniques have now been applied in multiple physics analysis carried out and physics measurements carried out with microBOON. But this is all work that has been done and applied offline, as I mentioned, with the luxury of being able to run your algorithms for as long as it's needed for training and inference, but also with as many computational resources as you can at will almost get your hands on. So can we do better? And in particular, can we do all of this data processing and data analysis online as the data comes in right out of our detector or in real time as we receive it? And doing so, applying these machine learning tools, AI tools, these intelligent data processing in real time or online on our full data output from the detectors also allows us to take a deeper look into the data, potentially with better decision speed, better latency, more computational power efficiently, but also with high accuracy as well. The ability to correctly identify what's in our data in real time versus not. And in this respect, DUNE represents both a challenge and an opportunity. It is a prime example of an experiment that is dealing with a massive data challenge in that it cannot possibly afford to record all of the data that its detectors will be generating over the course of its 10-year lifetime. This would be zettabytes of data. And I think from a couple of years ago, I don't know if this still stands, but at least a couple of years ago, this corresponded to 10% of the human generated digital data to date. Okay, so we can't afford to record all this data and then analyze it offline. We have to treat it more intelligently right as it comes through and sift through it as it's coming, and then cleverly identifying only the rare events that we care about. So the DUNE data acquisition system, in that respect, must make intelligent and prompt decisions on which data to keep, which are potential signals of interest, and which data to reject, which is simply background. This is often called data selection or trigger decision, and it's something that most particle detectors must do. And traditionally, only simple non-machine learning, non-deep learning algorithms have been used for data selection or trigger decision. But it would be great if we can adopt and adapt recent advances in machine learning and AI for real-time data processing and data selection at trigger level for the case of DUNE, especially leveraging the fact that the streaming data out of the detector are already very image-like, sparse image like. Okay, so let's take a look at the DUNE data acquisition system. So the detector in South Dakota is about a mile underground and is constantly generating 40 terabits per second worth of data. Now, this data must be down selected, achieving an overall factor reduction of 10 to the 4 before being shipped offline, before being shipped off-site for permanent storage, and then subsequent offline data processing at Fermilab in Illinois and at other international sites. And this down selection happens through several stages of processing, each one of which comes with varying latency, power, and data reduction requirements. In particular, there's 2 levels of processing, one which happens deep underground and is called a low-level trigger, and it can be real-time or batch processing. It reduces the data rate by about an order of magnitude before a second level of processing, the high-level trigger or high-level filter or high-level data selection, applies additional batch processing, reducing the data by an additional several orders of magnitude, about 3 orders of magnitude, allowing only maximum instantaneous rate of about 100 gigabits per second to be shipped off-site. But this cannot be afforded steady state. Steady state, we expect only about 10 gigabits per second worth of data to be continuously sent off-site from DUNE. In terms of the data flow, the data from the detector go through the upstream DAQ system, which does some basic pre-processing of data like noise removal before the low-level trigger stage occurs, and only upon a low-level trigger decision does data get shipped further into event building, and then an additional stage of down selection occurs as part of the high-level trigger before things get shipped to offline. But in particular, these 3 stages of data processing offer a combination of architectures, both field programmable gate arrays, FPGAs, and CPUs and GPUs, with increasing flexibility for both reconfiguring, but also using algorithms of increasing complexity, especially at higher levels of data processing. So these layers create opportunities of applying these machine learning tools for the purposes of data selection in DUNE and triggering in DUNE. So if we go back to the first stage, the low-level trigger stage, where the data comes out of the detector on a per wire base from each cell volume, There's first pre-processing of the streaming data that is carried out in upstream DAQ in FPGAs exclusively. And this is where denoising, for example, is applied on a per wire basis. Now, as part of this first stage processing, there's also lots of commercial CPUs that are available for low-level trigger. GPUs are also a possibility, but an important consideration is the power constraints that we have deep underground, as well as data I/O, how quickly this 40 terabits per second worth of data rate can be absorbed by GPUs and processed there. But the data that comes in and is fed into the upstream DAQ FPGAs can be rearranged in terms of sequential channel and time and into contiguous projection-like images of each cell volume in the upstream DAQ. And then the question is whether image classification can be employed as part of low-level trigger. And so this is something that we studied a while ago with a student who just graduated from my group here at Columbia. In particular, we studied the possibility of using a convolutional neural network to classify image frames, simulated image frames from one such DUNE cell in terms of three possible classes, whether it is an empty frame, whether it contains a supernova event, or whether it contains one of four possible types of high energy interactions. And what we found is that you can actually, by training such as CNN on 6 classes and applying a cut on the empty score cut, the empty class score cut, you could, with an increasingly stringent cut a lot more of the empty frames while still maintaining a fairly high efficiency to all your rare events of interest, the proton and neutron decay events, the atmospheric neutrinos, and even supernova neutrinos, individual supernova neutrino interactions. So you could get an accuracy of 90% for all interactions of interest with a background reduction factor of 140. So such a scheme could work quite well for the low-level trigger, meeting the needed trigger decision accuracy for the DUNE experiment. The question being whether we could also achieve the needed computational power efficiency and decision speed as well. So for this original study, we actually used a rather large network, a VGG16B, for image classification. And starting with the raw images, we downsampled them, resizing them from a 4450 by 960 pixel image to a 600 by 600 rectangular image before classifying it either in terms of six classes, or later on we devised a new scheme with just 3 classes: empty or background frames, supernova low energy rare events, or other high energy rare interactions. And what we found is that not only can you meet your trigger decision accuracy requirements, but also this ML-based scheme vastly outperformed traditional low-level trigger performance, particularly at low energy, below 10 MeV in neutrino energy, which is where you expect lots of your supernova neutrinos to lie. So the question then was, what about decision speed or latency of execution of the algorithm, and what about computational power efficiency? So we first considered the online inference time in GPUs, and for that it was clear that we needed to reduce the size of our inputs in order to meet desired latency requirements from 600 by 600 to 64 by 64 in input image size. we were still, by retraining a rather large network, able to achieve high accuracy, more than 95% efficiency in finding supernova interactions, and more than 90% efficiency in finding other rare high energy interactions, and very small misclassification rate of background only or empty frames. And we could do that with an inference time measured on a GPU, which was about 5 milliseconds for each input corresponding to an integration time in our video stream of about 2.25 milliseconds. And so this is for a frame that is coming from 1 out of the 200 cells. And so assuming a parallelization, at least 200 or 400 actually GPUs, then we could keep up with the data rate in terms of inference, at least. We were also able to show that faster online GPU inference is possible if we can make use of a smaller network. So instead of a VGG16 network, we devised a 4-layer CNN where we were able to train in a way so as to maintain efficiency to low energy supernova events, high energy rare events, but also ability to reject a high rate of noise or empty frames, and where the inference time was well beyond the integration time of our data frame, the 2.25 milliseconds. So we were able to show that with a smaller network, even much better improvement in inference time could be achieved. And this also met the latency requirements for DUNE. So the next question then was computational efficiency. And so for that, we turned toward power-aware hardware acceleration that involves the real-time implementation of machine learning algorithms in power-aware FPGA devices. So DUNE employs, as part of its low-level trigger processing, FPGA resources, in particular in the upstream DAQ. And so the question is, can we use some of these FPGA resources for real-time ML-based triggering? The advantages of using these FPGA resources is that FPGAs, in comparison to CPUs or GPUs, are much more power efficient, and they're also deterministic in the execution of logic, and how long it might take to reach a decision. The downsides being that they're not so easy to program or reprogram. They require the expertise of often engineers, and they also come with built-in hardware resource constraints. So if you're dealing with a fairly large network and fairly large input sizes, then you might be limited in terms of computational fabric, but also memory availability in your FPGA device. On the other hand, advancements in machine learning and AI and new tools and new technology provide an exciting possibility of hardware acceleration of machine learning algorithms, particularly for low latency real-time applications that do involve large data sets. And this is an exciting new development that's enabled by this new technology and tools. And this is a direction in which many particle physics experiments are turning, for not only DUNE, but also the CMS experiment at the LHC, other, for example, balloon or satellite deployed instruments such as GRAMS, or deep underground dark matter detectors such as Xenon. So as a first step, we partnered with collaborators in computer science here at Columbia, and we tried to explore that same small 4-layer network that I mentioned earlier on a system on chip that employed both FPGA and CPU resources on it, and compare the power efficiency and energy efficiency between the two of them for the same algorithm and execution. And we saw that the performance when leveraging the FPGA for acceleration was improved with an almost factor of 2 increase in average speed up for inference, and also a factor of 2.5 more power efficiency with respect to the software implementation on the CPU on the chip. So indeed, we were able to show early on that there's a huge advantage in employing FPGAs in terms of computational power efficiency. But especially if we want to reuse only available FPGAs in the DUNE design that are part of the upstream DAQ, an additional concern is the resource footprint of the CNN if we were to implement it in FPGA. So for that, we turn to other tools made available through recent advances within the community, in particular HLS4ML tools that allowed us to flexibly evaluate resource utilization on a variety of FPGA chips in general. But what we studied in particular is the planned Xilinx UltraScale Plus FPGA that is planned to be used for DUNE. So we studied specifically the implementation of a relatively small CNN, which we also downsized and further optimized with Keras tuner to reduce computational footprint, and also trained using quantization awareness. So this was a quantization aware trained, relatively small CNN that we were able to train in order to meet the accuracy specifications of the DUNE low-level trigger. So achieving efficiencies toward individual supernova interactions of almost 95% and high energy rare events of interest of greater than 9%, while still being able to reject more than 99.5% of empty frames. And additionally, we were able to estimate resource utilization on the DUNE FPGA for such instance of the CNN running and processing a single frame, where in particular the quantization aware trained version of the CNN made use of the lowest amount of resources, 4% of RAM, 38% of DSP units, 10% of flip-flops, and 20% for lookup tables of the FPGA, and still gave us a relatively low, also efficient latency of 25 microseconds when employing significant level of pre-processing of the input frames from each of the cells. So we were able to then show overall that both accuracy, computational power efficiency, but also speed of execution can be met with existing resources in DUNE. And this is really an exciting development because employment of such intelligent algorithms right at the data source allows DUNE to develop a much more enhanced astrophysics program. The ability to select a large sample of supernova neutrino candidates in real time offers the possibility of also additional prompt studies of directionality. So in that sense, DUNE can not only see that there's supernova neutrinos interacting in the detector, but it can also take those and analyze those with higher confidence and take a stab at guessing where those neutrinos are coming from, and be able to point toward the supernova source. This can be done by making use of different types of neutrino interactions for supernova neutrinos. So the majority of events that we expect to detect are from electron neutrinos interacting with the argon nucleus and producing an electron and an excited potassium atom, which then excites, producing these gamma rays, which produce the MEV blips in the vicinity of the interaction. But there's also another type of interaction of neutrinos, which happens with any kind of flavor of neutrinos, where they interact with atomic electrons. And there you don't have visible blips, but you have still an electron, and the direction of this electron is much more correlated with the original direction of the neutrino. So even though this electron can come out at pretty much any angle, on average, it will point back to the original direction of the incoming neutrino. And so the ability to find these events within our sample of supernova neutrino interactions allows us then to provide accurate and precise reconstruction of the outgoing electron direction, and then on average be able to point back to the supernova source. So I showed earlier that we're able to find supernova neutrinos of even lower energies with much higher efficiency by employing ML-based triggering. But additionally, one can employ ML algorithms for classifying the type of supernova interaction, or whether it's a charge current interaction or argon, or elastic scattering with an atomic electron. And we can also perform regression for determining the electron angle as well for pointing. Now, overall, the enhanced trigger efficiency for low energy neutrino measurements also offers the possibility of moving to lower in neutrino energy towards solar neutrinos. And in this case, if we can detect neutrinos of just a few MeV, then we have access to boron 8 neutrinos produced in the sun, or AGP neutrinos produced in the sun potentially. And that also allows us to study neutrino oscillations associated with flavor transition in the sun, or other non-standard neutrino physics that might affect neutrino propagation in the sun, and then also effectively study the solar model. I should mention that this is all an exciting possibility, but there are of course all these considerations that I made, not just cost, power usage, longevity and reliability of hardware, but also in the case of using deep learning tools, machine learning tools, reliable inference always requires accurate and realistic simulation for training our algorithms. And this is challenging or impossible even when searching for new physics, for signatures that you don't even know how to begin to simulate to begin with. So these online data selection trigger applications require the ability to, in addition, I should say, the online data selection trigger applications also require the ability to adapt and remain robust against changing detector conditions as well, in lack of being able to understand your data quite well. And so because of this, validation of performance with real data is imperative for these techniques, but also consideration of alternate methods, for example, anomaly detection for triggering is something else that should be explored. So these are all some caveats that I think all of us who are working in this direction always keep in mind. But actually there are opportunities for exploring new and perhaps more intelligent methods of sifting through data. So this is my summary, very briefly, since I think I'm out of time. Today's particle detectors stream raw data with increasingly high resolution, volume, and complexity, posing a data processing and analysis challenge. There's the particular detector technology, that of liquid argon time projection chambers, which is employed by the future DUNE experiment, which is unique in that it allows for ideal applications of machine learning for image analysis for the purposes of real-time data selection and triggering. And there's ongoing developments which demonstrate the viability of such triggering in DUNE and invite further exploration of such application. And FastML can enable a deeper, more detailed look into particle physics data sets, and in turn, fundamental physics discoveries in particle physics. So thank you for your attention and this invitation again.
Thank you very much, Georgia. That was a fantastic talk. Really, really appreciate it. We probably have a bit of time. We're a little bit over, but maybe we could take a question or two if anybody has one. Please raise your hand if you have a question. So actually, I have one. So this is just a question generally about what's known about the noise and the background in general. Do you think we have adequate samples right now from proto-DUNE and micro-DUNE and so on to reasonably evaluate what the possibilities are now, or is it really going to take more than that?
Yeah, this is a really great and very key question. Of course, we can have some idea in general of how these algorithms perform in terms of our ability to train them on simulations and then actually go test them on real data and see if they fail miserably, require a complete rethink of the situation, or whether there's things that we can do to tune these either our data or the algorithms themselves to make them less sensitive. It's really important that we start testing these with existing detectors. Now, of course, every detector is unique. It's built with a different grounding scheme, is built with different electronics sensors, is subject to different gains and different noise levels. And so the same kind of checks and cross checks and validations that we would do before convincing ourselves that, you know, this particular ML or DL algorithm works for this detector on both data and background, we would need to repeat them ultimately for DUNE in situ.
All right, thanks. Any more questions or comments? Oh, one question from Tom.
Yeah, it's actually almost the same question, but what happens if the noise changes? You had talked about being robust to changing detector conditions. And I guess what often happens is that the trigger rate may go up if the noise goes up, but the efficiency stays the same if you've got a dumb trigger algorithm that doesn't learn on the fly. But if it does learn on the fly, then maybe your efficiency will change. And what's better for analysis is, do we want the data to have uniform efficiency or uniform trigger rate? What's the figure of merit here?
That's a good question. So from a practical standpoint, what you can do in anticipation of, you know, noise changes is you can train your algorithms with varying noise levels or varying models of noise as well, just to ensure that they're insensitive to such fluctuations that you might expect, you know, up to the level with which you can predict what those fluctuations might be. Now, in terms of whether experimentally we would prefer our trigger rate to stay constant versus our trigger efficiency to stay constant under such fluctuations. So there are often hardware limitations where our detectors cannot absorb trigger rates above a certain amount. So, you know, if you're not able to design a system that can handle fluctuating trigger rates with the intention of keeping your efficiency constant over time, then in that case, you inevitably have to take, for the example that you gave, a hit in efficiency because you can't possibly absorb a higher bandwidth of data. I would imagine you don't want your efficiency fluctuating as a function of time. That affects, you know, your operation plans, how long you want to run for, to gather a certain data set. Yeah, it's an interesting question I hadn't thought about before.
Okay, thanks.
Others can comment also, I should add.
Right, more questions or comments? All right, if not, then thank you again very much, Georgia, for that beautiful talk. And thank
Thank
you
you.
to everybody for attending. See you next time.